Hello everyone. In this video, we're going to discuss what matter is, how to define it, and then also how to classify the different types of matter that exist. So, with regards to chemistry, chemistry is the study of matter and how matter changes. But the question we need to answer before we go any further is what exactly is matter? How can I define matter? What does it mean for something to be matter? And what does it mean for something not to be matter? So in order for something to be considered matter, it has to have two qualifications. First thing, it has to have mass, aka I have to be able to measure the amount of that substance that exists. So if I have a scale, for example, I can put that piece of matter on the scale and I can figure out what's its mass. Usually the unit that the SI unit for mass is kilograms. However, keep in mind the SI applies for all sciences, not just chemistry, so kilogram can be a little bit large, and if you're in a chemistry lab, you don't want to use a lot of material for a variety of reasons. So more commonly than kilogram, we like to use grams. So you'll see me discuss grams a lot, but keep in mind the SI unit for mass is kilograms. The other piece that matter has to have, it has to take up space. The term we use to describe something taking up space is that it has to possess volume. Now, volume is the definition term for that. Typically, if we do it in some sort of formula, you'll see volume represented by a capital V. Capital V for volume. Now, let's talk about some examples of matter. Liquid water. You can see that right here. Solid desk, maybe the desk you're working at. An example of a solid is right there. And the air that you're currently breathing, that's gaseous air. So you can see that in this Erlenmeyer flask here as well. Now, you can probably think about everything that you interact with on your day-to-day life, your shoes, your toothbrush, your food, things like that. Those are all examples of matter. But what isn't matter? Because that kind of, helps us distinguish from what we have to define things, knowing what it is and then what it definitely isn't. So some non-examples that I've compiled here. Space, the idea of just space in general. We understand that volume is necessary to define matter because volume is the amount of space something takes up. But just because there's space doesn't mean there's mass, right? So the idea of like outer space or just space in your house and things like that, those are not examples of matter. When you go to sleep and you dream, that's not matter. You can't measure its mass. You can't identify how much space it takes up. Magnetism, the idea of something being positive and negative and there's forces occurring between those two things, again, doesn't have mass, doesn't take up space. A lot of abstract concepts like time, how long something takes, again, that doesn't really apply to mass or volume. And then one that kind of throws people off a little bit is energy. Energy does not necessarily have mass and take up space. It's a totally different measurable quantity. So as a result, we don't classify things like energy or heat or something like that in terms of matter. Now, in previous chemistry courses, you'll typically hear that there are four states of matter. There's solid, there's liquid, there's gas. The fourth one is plasma. However, plasma is basically just ionized gas, which means if you take electricity and you shoot it through some gas and you get those gas particles really excited and kind of elevate their energy, that is what creates plasma. So we're not going to cover plasma because it's not really practical for a beginner chemist's standpoint, but it's important to know that there is four, but really for the purpose of this course, we're only going to study the three. Now, how do I differentiate between solids, liquids, and gases? You want to look at two things. You want to look at how is the shape of that matter, and then second, you want to consider how the volume of that matter is. So if we look at solids, for example, so I'll make a little mini chart here. How do solids look? If you look at the shape of a solid, it has what's called a fixed shape, or often you'll see it as a definite shape. So I'll put a little D here for that. So solids have a definite shape. If you look at any piece of solid, you can tell at that point in time what its shape is. For example, with this cube here, we can identify how many shapes it has, and it has a discernible shape. If I were to rotate this Erlenmeyer flask even 5 degrees, the shape of that solid is not going to change. The solid stays the same. Now, of course, there's some solids that are brittle, like salt, for example, big salt rocks, those can break very easily. Maybe you have something like silly putty, right? But the thing is, it's like if you were to do a change to that, just like a piece of paper, if I tear a piece of paper, the shape of that paper still really isn't changing because, I mean, yeah, I tore it in two pieces, but the shape is still constant. I can flutter it in the wind, I can do other things with it, and it's not exactly changing, okay? And the volume, or how much space it occupies. So we can actually calculate the volume for this, and since the shape isn't changing, really the volume isn't going to change either. So we can say that the shape is definite, it's defined, the volume is definite as well. Now liquids is where things get a little bit different. Typically we represent liquids with a little cursive L, by the way. Solids are usually in parentheses like that. Liquids are usually like that. Now what about the shape of a liquid? Well, if I were to take this liquid, and let's say I transfer it to a beaker. So a beaker kind of looks like this. It's basically the one that is the most common transferring device in chemistry. It's easy to pour things because there's usually kind of like a little pour spout right here. And there's little markings on it typically to indicate how much volume is present. If I were to transfer this liquid into that beaker, and the beaker is a different shape than this, it's going to change the shape, right? Because just because it looks like this now, if I put it in here, maybe it'll look something like this, right? Where it's going to maybe take up less height but more width, for example. So we would say that the shape of liquids in this case is indefinite. Indefinite meaning that it can change, right? So we like to use indefinite for that. Where'd my clicker go here? There it is. It's indefinite. Okay, so we put an I there to represent indefinite. Now what about the volume? Let's say, for example, I have 50 mils meaning milliliters, so I have 50 milliliters of water here. If I were to pour that water in a beaker, would I expect it to still be 50 milliliters? Yes. Let's say I put it in a bigger beaker. Let's say I put it in let's say we put it in a graduated cylinder. This is kind of a really fat graduated cylinder, but those exist. Let's say I put it in a really big one. It might occupy what appears to be less space. However, because it's wider, and we have to recognize that, there's different sizing here, it's the same amount of volume. So the volume here is going to be definite. So liquids have an indefinite shape. It can change based on what container you put it in. 50 mils of water in this Erlenmeyer flask will look different than 50 mils in a water bottle or 50 mils in a pool. But the volume should remain the same. Now let's go to gases. That's our third type. Okay, I'm running out of space here. I guess I'll kind of do it over it. Gases typically are represented by parentheses with a G. What's unique about gases is that no matter what container they're in, they will expand to fill that container. So if I have the gas in, let's say, a CO2 tank that people, if you ever play paintball, they're usually like these little CO2 tanks that kind of look like this. And they kind of attach to the end of the paintball gun. Right now, this is pressurized gas in here. So gas particles are moving all over in here. If I were to push down the piece there and release it out into the air around, that gas is not just going to kind of stay in a bubble. It's going to move rapidly and expand to fill the size of the room. Let's say I did this in my house and it's trapped in my house. If I open a window, now that CO2 is going to release and then fill up the air in the outside. So it'll go into the outside world. So the moral of the story here is gases expand to fill their container. Well, if they expand to fill whatever container they're in, if I put this in a CO2 tank that's small, and then I put it in a bigger one, for example, would that shape change if it expands to fill the container? Yes, the shape would change. So this is an indefinite shape. I for indefinite. I'll put it over here so you can see it better. I for indefinite. What about the volume? If it expands to fill the container, if I were to transfer containers, and one's bigger than the other, is the volume going to change? Yes, the volume should change. So we would say that it's an indefinite or, unfixed volume as well. So I'll put I for indefinite here. So notice the three different states of matter, they have different methods for how they behave, and that's one way we can identify what state or what phase they are in. Now, one way that chemists can accurately represent states of matter on a microscopic scale is using what's called a particle diagram. You'll see these a lot on your exams, and if you ever go on to study chemistry past this class, you will very often have to represent particle diagrams. Why? Because they're simple for people to understand. If you were to look at this huge glacier in this picture here, there are hexillions upon hexillions upon hexillions of water molecules in that particular glacier. It is such a large number that to humans, we can't imagine anything of that magnitude. It's like if I said you have a dozen eggs, you can clearly picture in your head what a dozen eggs looks like. But if I wanted you to picture 6.02 times 10 to the 23rd, that's essentially 602 with 21 zeros at the end of it. It's a lot of zeros. You have never seen anything in your life with your two eyes that can quantify to that value. It's really hard to understand and hard to grasp. So what chemists do is in what's called the microscopic domain, which is essentially where all chemistry occurs, right? It's these little tiny atoms and these tiny molecules behaving differently to make macroscopic changes that you can see. So often we'll try and draw them on a very small scale. Now we know that in the air around this particular glacier, if we look at water vapor, again, why is it water vapor? Because it's H2O, and then we have the G for gas here. So I know it's a gas, it's a vapor. I know that there's not 6 gas molecules around the entire thing, but showing the spacing here between these really gives us a good idea as to, you know, how they occupy space. And then also you might see arrows drawn off these too, indicating that they're moving at a rapid pace. Often those are translational arrows. I'll write that down, that vocab term, translational. You have 3 types of movement, by the way, guys. Translational, this is a little bit of a tangent. You have vibrational, and you have rotational. So with gases, you'll see translational, you'll see vibrational, and you'll see rotational. You'll see them all. Solids, we like to think that solids don't move, but they actually do move. Solids vibrate upon a fixed point. So these structures, notice how they form nice patterns, right? This looks like a hexagon here, it looks like a hexagon here, it looks like a hexagon here. You can expand that forever, and that's how solid water is going to look. Also, it's commonly known that, glaciers are going to kind of float on top of the water because they're less dense. Notice how there's all these air pockets in here that are going to allow that ice to be less dense than your liquid. That's why if you drop a couple cubes of ice in a glass of water, it's going to float to the top, because solid is less dense because there's a lot of air in between it. Now, they're pretty close together. In the case of water, because it's a crystal structure, it's a lattice, it's going to look a little bit more spread apart. But most solids, like if you think of metals, they're going to have circles that are very close to each other and often making contact in a nice, even kind of layer like this. Okay, so solids typically like this. Because this one's a crystal lattice structure, it's going to be a little bit more spread out. But again, in terms of movement, solids, that's going to fall in the vibrational category only. So I'll draw little lines here so you can see a little bit better. There we go. Now liquids, those are going to move translationally. They're basically going to do the same thing the gases do. They're going to move translationally, so they're going to move past each other, side to side, up, down, left, right, those types of motions. They're going to move vibrationally. They're going to vibrate slightly, and they're going to rotate as well in many cases too. So again, liquids are a little bit more spread out, so you might see them kind of look like this. Maybe some are making contact, but they're pretty close together, but they're usually a little more spread out. The gases are the ones where you'll see them like really spread out and often really moving with these little arrows. Because again, liquids, if they change shape, they have to be able to move freely. So that's particle diagrams of all 3. Now let's classify matter into broad, understandable categories. We're going to focus on pure substances in the first couple of slides. We'll focus on mixtures in some of these later slides. Oh boy, where'd my clicker? There it is. So, classifying matter. We have 2 broad categories. We have pure substances and we have mixtures. Just as a general rule of thumb, you're going to see many mixtures in your life and many mixtures in chemistry. Pure substances are much less common. For example, the tap water that you're drinking right now, this cheap stuff, that's like not that much money, that's not a pure substance. That's a mixture of water and other fortifying agents. Pure water, just H2O, that's a pure substance. Now, how are they different? Pure substances have what we define as a constant composition. What that means is if you have a pure substance, let's say pure water, H2O, it is always going to be H2O in that ratio, in those proportions, in that composition, percentage by mass, every time. So they're going to have the exact same chemical makeup, and as a result, they're going to have the exact same properties as well. So let's take sucrose an example. Sucrose is a type of sugar. If you were to look at sucrose will always have 42.1% carbon, that's what that C stands for there on the periodic table, 6.5% hydrogen, and 51.4% oxygen by mass. So what that means is if I had a 100-gram sample of sucrose, you can basically turn these percentages into grams. So out of 100 grams, 42.1 of those grams is carbon, 6.5 grams is hydrogen, and 51.4 grams is oxygen. Keep in mind that no matter what amount of sucrose I have, if it's pure, they're going to have the exact same physical properties. Some examples of physical properties, they'll have the same melting point. So sucrose will turn from a solid to a liquid at the same temperature every single time. They'll also have the same color as well. And there's other physical properties as well. But again, we'll get to that later. Let's go through pure substances. So to kind of further break down our tree, so you can kind of think of a tree map here, we have two types of pure substances. We have elements and we have compounds. Elements are the simplest form of a pure substance and really of matter because they really can't be broken down into anything any simpler. Now we know from previous science classes that, elements, or like if I take, for example, one atom of oxygen, there's going to be some number of protons, some number of neutrons, some number of electrons that make that up. However, it's very tough to just split that up. I can't really identify and give something physical properties that's any simpler than an element, for example. So an easy way to identify an element versus a compound, and something that you should hopefully know by now, is you want to look for the number of capital letters. So let's see here. Get my pen back. I'm losing it. Okay, capital letters. So lithium is an element on the periodic table. How do I know lithium's an element? I have a capital L, a lowercase I. Gold, very popular element, very expensive if in the pure state. Capital A, little u. Carbon, capital C. Oxygen, capital O. The list goes on and on. You'll always ever notice just one capital letter. Compounds, however, are a combination of multiple elements in a fixed whole number ratio. So water, for example, is H2O. What that means is that in every molecule or every compound of water, I'm going to have two hydrogen atoms, or two hydrogen elements, you could say, two amounts of that, two hydrogen atoms, one oxygen atom. Okay. If I think of CO2, another one that you're very familiar with, that's one carbon, two oxygens. Notice there's multiple capital letters here. Okay, so that's one way you can determine an element from a compound. Oh, another thing, the only way you can split up a compound is through a chemical change, which we're going to get into in more detail later down the line, but chemical changes are the only way you can split up a compound. Elements cannot be broken down any further. These can be broken down by chemical changes. I listed it right there. All right, let's talk about mixtures. Again, mixtures, these are the more common form of matter that you'll see in everyday life. A mixture is composed of two or more types of matter that can present in varying amounts and can be separated by physical changes. So again, this is different than compounds because compounds, you have to do something chemically to them. Physical changes, you can separate mixtures. So some examples of that, you can have evaporation, you can have boiling, so simply heating up something or cooling something down might allow you to separate it. A couple other techniques that we're going to get into later in the course. You can distill it, or a process known formally as distillation, which basically uses your knowledge of boiling points to separate different liquids. You could use something called chromatography, which we'll get into in our states of matter chapter. which is a means of chemical separation based on different forces at play. So these are other examples of physical changes. Filtration's another one. Filtration. Okay, you can do filtration as well. So basically taking something that has a solid and a liquid mixed in, you pour it through a filter, it separates it out. So we have two types of mixtures. The main difference in these is that it's the type of, or not the type, the number of layers, or what's called the number of phases. So if we think of prefixes here, because that's really the only things that separate these two words, hetero versus homo. If you think of hetero, that usually means two or more. Okay, and that's usually two or more layers, or you can identify two or more distinct, phases in that state of matter, or in that mixture. Homogeneous mixtures, also known commonly as solutions. So anytime somebody throws out the term solution, they mean a homogeneous mixture. That is only one layer or one phase. So basically, when you look at a homogeneous solution or a homogeneous mixture, it is going to look a lot like a pure substance, because you can't tell that there's multiple things combined. It looks like just one thing. Here's a picture to illustrate that. This is an example of a heterogeneous mixture. Pardon my bad handwriting. Notice we have two layers here. This is a salad dressing mixture here. You have oil droplets here. Notice the circles, those are oil droplets. And then you have a red colored solution around it. This is essentially me taking acetic acid, vinegar, and taking oil, some sort of unsaturated fat here, and basically pouring it in, and we'll have distinct layers. You can tell looking at this picture, that's oil, that's vinegar. These are in a lot of your salad dressings and different things like that. Solutions, they look like one thing. You cannot tell that there's anything mixed in here because it's so uniformly distributed that you really can't tell. Now, one thing I want you guys to understand, and again, this is a homogeneous mixture. Okay, it doesn't have to be liquids and liquids, right? If you think of like Gatorade and stuff like that, oftentimes you can have solids and liquids mixed together to give you mixtures. You can have liquids and liquids. You can have gases and liquids. For example, if you have a carbonated beverage, that's CO2 being dissolved in water. So again, that's another type of mixture you can have. You can have solid and solid. That's called an alloy. So if you ever have any jewelry, you're not wearing a ring that's 24 karat gold. It's usually some gold and some nickel and some other things mixed in to make it more fortified, more strong. So you can have really any combination of two states of matter. Gases and gases is another one. Because if you think of the air you're breathing, that's a gas-gas mixture. You've got water vapor, you've got CO2, you've got oxygen, you've got nitrogen. Those are all a variety of gases being combined together. So a lot of different types of mixtures. Now you might get to a point where you might have to identify the different types of matter. Maybe we have to distinguish between a mixture and a pure substance, for example. So if we're ever in this type of situation here, we really want to follow the flow chart. First question we have to ask ourselves, does it have constant properties and composition? AKA, if I have a sample and the properties don't seem to change based on the amount that I have, and if I find, the percentage of whatever makes it up, is that composition always the same? If yes, you have a pure substance. If no, you have a mixture. If you have a mixture, then we have to ask ourselves, well, how does that mixture look? Is it uniform throughout? AKA, is it evenly distributed? Can I identify multiple things in that mixture? If I cannot identify different things, is it uniform throughout? It's evenly mixed? Yes, it is. Then it's a homogeneous mixture. Is it not uniform throughout? Can I identify a bunch of different stuff? Then it's heterogeneous. Now let's jump over to pure substances, because now I have to determine, okay, is it an element or is it a compound? The only way you can determine a pure substance is through a series or a single chemical reaction. So, can it be chemically separated? Elements, remember, these are the simplest things, right? These are super simple. You can't split up AU into anything else. You can't split up carbon into anything simpler. If you can't chemically simplify it or separate it, you have an element. If I have a compound like H2O, I can add a little electricity to this, little thunderbolt there for you. I can add a little electricity, and I can get H2 and O2, for example. We'll balance that out to make it look better. Can I separate water into H and O? Yes. Can I simplify it? Yes. Then you have a compound. So that's basically what matter is and how you can classify it.